when we talk about energy in terms of chemistry, right? We're gonna often think about that in terms of heat, so we're gonna associate with the heat that's being generated, okay? So if we think about it, let's see here. So we know that water boils at what temperature? So let's say this is the curve for water. What temperature does water boil at? You should know this from chapter 3. If you don't know this, then you're not looking at your notes. Chapter 3, come on now. Water boils at what temperature? In Celsius. Say it again. 100 degrees Celsius. And water freezes at what temperature? 0. So you guys do know this. It's being difficult. Okay, so we know that we're in the liquid phase if we're below 100 degrees Celsius, right? As soon as we get to that 100 degrees Celsius, we start going into the gas phase, and we start to evaporate, right? So in this case, this here represents the energy curve, what's happening. So at 0 degrees Celsius, we'll talk about that one, it's a little easier to understand. So when it's frozen, right? If we're at 0 degrees Celsius and we're below 0 degrees Celsius, it's going to be frozen. It needs a little bit more energy to sit there and get over the hump to start becoming liquid. Okay? It'll still be at 0 degrees Celsius and you'll start to get liquid forming at that stage. We'll notice that some of your water will be at 0 degrees Celsius because it hasn't quite made it over that hump to completely get over that, into that phase. Once it gets over that hump, then we're into that liquid phase. Okay? And so when we're talking about the heat, this will be the heat of fusion. This will be the heat of vaporization. That's going to be represented by this hump because it needs to get over that energy level to start getting into that next phase. Okay? And that's the same thing down here. It needs to get over this hump to get into the next phase. Okay? And so this value, we make reference to delta H. So we'll have delta H vapor. And we'll have, or delta H fusion. Okay? So this is representing the amount of energy that it takes to get over a hump. And it's based upon your quantity or the mass of what you have. So it's going to be based upon your quantity and mass that you have. So the units that you're going to have for these, it's going to be joules per mole or joules per gram. And when I say joules, it can be kilojoules or it can be microjoules or millijoules or whatever, but just the concept of having that unit. So that's what you typically see. Or you'll see in the US, you'll see calories. Calories per mole. Or calories per gram. Okay? So if they give you the mass and they give you the units in joules per gram, you know it's in grams. But if they give you the number of moles, right, then you know you're going to use moles. Or if they ask you how many moles of something, that typically is an idea that we need to change our grams to moles. Okay? So, when we talk about this region here, this region is going to be dependent on, and this is the symbol for heat is Q. This is my little Q. And then it's going to be M, meaning mass. C, delta T. Now C is called heat capacity. or specific heat capacity, okay? Now, it's going to vary from what we're working with, because when we're in different states, we're going to have a different ability to retain heat, okay? And so that heat capacity is the amount of the ability that it retains heat. And so then that'll help us calculate how much heat can be given from this particular element or this particular element in this particular phase. So for instance, if we talk about our heat capacity for ice, okay? So we'll have a value that's given for that specific heat capacity of ice, okay? And you guys remember what delta T is? Don't remember what delta T is? Did you guys look at chapters 3? The end of chapters 3? Pull out your notes from chapters 3. Okay, so our delta T represents the difference in temperature, right? Delta T equals difference in temperature. Know that N is mass. And then, so usually our specific heat is going to be given to us to some value. For some reason, I can't remember. I know the specific heat of water. So water is, I can't remember ice at the top of my head. Specific heat of water is going to be 4.184 joules per minute of water. Okay, so let's kind of play with this. Okay, so let's assume that we're just going to calculate our Q value for water. Okay, and so let's say our water is going from 5 degrees Celsius. So to 30 degrees Celsius. Okay, so if we want to calculate the heat, or we're making reference to energy that's being generated if we go from 5 degrees Celsius to 30 degrees Celsius. And let's assume that we have zero, stay. So assume that we have 10.00 grams of water. Okay. So I'm going to erase this part here. So in this case, what we would do is we plug in our mass. Okay, we have our heat capacity for water, which is 4.184 joules per gram. And then we plug in the difference in temperature. So our final temperature is what? 30 30. And our initial temperature is 5. Okay, and so that's going to give us our delta T value. So remember, this is just T final minus T initial. Okay? So then our Q value is going to be equal to what? Q value is going to be equal to what? Are they 30? What does it say up here? What was that? Yeah. And then that's going to be multiplied by 30 minus 25. So, I mean, 30 minus 5, which is 25, right? So, we have 10.00 grams canceling out. That's degrees Celsius. I forgot. Celsius. Times 4.184 times 25. You guys end up with. Okay, how many sig figs do we have? And our units are joules, because it represents energy. How many units? I mean, how many significant figures do we have? Not units. 4, are you sure? 3. So why is it 3 and not 4? That's at 25, right? So then that's 1,050. Okay? So this helps us understand that concept of heat. So when we're moving from one temperature to the next temperature, it's generating a certain amount of energy, right? Or it's going to take a certain amount of energy to sit there and get that to happen. That's how much energy it's going to take to go from 5 degrees to 30 degrees. Okay? They're kind of comparable. How many of you guys have a significant other? Boyfriend, girlfriend? Okay. 2 of you guys. That's it. So a lot of you guys are single. Is that what I'm hearing? Single, ready to mingle. Is that what I understand? Okay. So, have you ever had a boyfriend or girlfriend? Anybody? You have. Okay, have you guys laid together, cuddled, all that stuff? You guys did that before? Okay, now, typically in a relationship, you have somebody who's hot-blooded and somebody who's cold-blooded, right? Typically. Which one are you? Are you hot-blooded or are you cold-blooded? You're cold? So you're always cold? You're cold? Always cold? Are you cold? You're hot, okay. So, there's always the person who's cold is gonna put their cold body on you. They'll put their cold feet on you and everything like that. And what do you do when they do that? Since you're a hot one. what do? You push them away, right?
Yeah.
So why do you put your cold feet or your cold hands or your cold body on that other person? What was that? To be warmer. And so what do you think is doing it to them? What's happening to them? Why do you push them away? Because you're getting colder, right? So what happens is, in terms of heat, when we're talking about heat, heat is going to be transferred, right? So if we think about reactions, a reaction is going to be using its environment, right? So like, if you're the cold person and your boob is bigger than you, he's the environment. You're going to be stealing heat from him. He's going to be upset because he's going to get cold because you're cold and you're making him cold, right? And so what happens is you're transferring heat. And you guys are going to meet somewhere in the middle. So if I have a really hot piece of metal and I have a really cold water bath, what happens when I stick that hot piece of metal in that cold water bath? The metal cools down, and then the water starts to do what? Starts to heat up, right? Okay? So the water heats up, and the metal cools down, and they'll meet somewhere in the middle. Okay, that's part of heat transfer. So like if you're in your boat, you guys are meeting somewhere in the middle. You're getting warmer, he's getting colder. So that's why he's getting mad, because he's like, man, you're cold, right? Okay. So that's the transfer of heat. So that's also helps us understand what happens to energy, because heat is just a form of energy, right? Energy is never lost, it's just being transferred. Right? So we're either transferring it to another form or we're transferring it to something else. So it's never lost, it's just transferred. Okay?
How did you find the 4.18?
That's typically given to you. It's always going to be given to you, or you're going to calculate. One or the other, right? Give me anything else. And I'll give you some more examples in a minute. Okay? Okay, so when we're making reference to temperatures changing, we have to take into account temperatures changing. Right? So, but we have to be within that phase. Okay? So if we're out of that phase, we also have to start taking other things into consideration. Right? So the heat capacity, this value for C, is going to be different for ice than it is going to be for water. It's going to be different for steam than it is going to be for water. So we have to make sure that we're aware of the phases that we're going to be in to sit there and distinguish what we're going to be using. Now let's say we're going across multiple stages, which I'm going to show you here in a minute, then we're going to have to take a couple of things into consideration. Okay? One of those things that we have to take into consideration is the heat formation. The energy that it takes to get over the hump. Right? That delta H. The other thing is that we're going to take into consideration this phase and that phase. Okay, so let me show you what I'm talking about. Okay, so key terms: heat of vaporization, boiling point. Okay, so you guys can actually see behind me. So when we talk about that heat of vaporization, right? So that represents the energy that it takes to go from a liquid to vapor. Now, that process is going to be endothermic, right? So you're having to put energy in to make that happen, to go from a liquid to a gas, right? Now, for us to go the opposite direction, that's going to be an exothermic reaction, right? What does endothermic mean? What was that?
Inside?
Inside, yeah. So we're putting energy inside. So in the case of going from a liquid to vapor, we have to put energy in to make that happen, right? But for us to go from a vapor to a liquid, that means that energy has to be released. It has to get rid of some of that energy, okay? And so, but that process of heat of vaporization and the heat of condensation, they're gonna be equal to each other, but they're gonna be opposites. One is gonna be positive and one is gonna be negative. If it's endothermic, we're putting energy into the system. So then it's gonna be positive. If it's exothermic, we're taking energy out of the system. So then it's gonna be negative. Okay? Right on the board. And these are some of those things that you may want to write down, you know? So endothermic is going to be positive, and this guy is going to be negative. So if we talk about that boiling process, we're at that point going from a liquid to a gas. And we need just that amount of energy to get over that hump. Once we start getting over that hump, then we start getting those bubbles coming out. So we start getting that gas coming out. So once that molecule gets over that hump, it's able to be released and go into the vapor. Okay? Okay, so this is how we are going to look at the heat of vaporization. So the heat of vaporization is just a form of heat, right? So then we're going to say Q is going to be equal to delta H vape times mass, or it could be moles, right? So it can be either N or M. We use N for the number of moles.
Q is energy.
Q represents energy or heat in general, the overall heat. Okay? So, if you look on this paper here, this basically gives us the values for the heat of vaporization. I'll write them on the board so we'll have them. I can erase this, everybody got this down. Right? Okay, so how to use the ability to get over that hump is, this is basically a problem where we're going from a liquid to a gas, okay? And so they want to know how much energy is needed to vaporize 188 grams of a liquid if its heat of vaporization is 1.13 kilojoules per gram. Okay? So, in this case, all we're looking at, we're not going from one temperature to the other, we're just looking at the ability to get from that hump. So you're right at that point that the line between a liquid and a gas, okay? So in that case, all you're going to do is your Q is going to be equal to delta H vape, and then you're going to be multiplying it by the mass. So mass or number of moles. Okay, so in this case, we have Q is going to be equal to M delta H, okay? Where our delta H vape is what value? vaporization in the problem. That was kilojoules per gram. Our mass, 188. Okay, so then all we're gonna do is just plug it directly into the equation. Get 188 grams times 1. Okay, so you guys did that. So 304.
No, 304.
212 kilojoules. Okay. Questions? And so again, when we look at this, this is only representing this line right here. Right? It's just getting over that line. Okay? Going from the phase, from a liquid phase to a gas phase. That's all it represents. Okay, so when we're talking about the energy involved in changing from states to states, right? If we start with the heat of fusion, the heat of fusion is going from a solid to a gas. The heat of solidification, that's going from solid to a liquid. The heat of solidification is going from a liquid to a gas. A liquid to a solid. Man, I need a little more coffee. It hasn't kicked in yet. It's too weak. Okay, so we know that they're going to be equal to each other. So if we're going from a solid to a liquid, the value is going to be the same, but the difference is going to be the charge, right? So going from a solid to a liquid, are we putting energy in or are we taking energy out? So if we're going from a solid to a liquid, so do we have to make it go from a solid to a liquid, do we have to put energy in or do we have to take energy out? Okay, we have a block of ice, right? A block of ice, okay? Now, if we think about this ice, if I put energy into it, what's going to happen? So I put a little heat into it, what's going to happen? It's going to melt, okay? So isn't that going from a solid to a liquid? Okay, so am I putting energy in or am I taking energy out? Okay, so if I'm going from a solid to a liquid, I put energy in. So then is that going to be a positive value or is that going to be a negative value? Positive. Okay. Now, if I'm going from a liquid to a solid, am I putting energy in or am I taking energy out of it? I'm taking energy out. So if I'm taking energy out, is that going to be positive or negative? Okay, so the heat of fusion is going to be a positive value. The heat of solidification is going to be a negative value. They're going to be the same value. Okay, but it's just whether they're positive or negative. Okay, does that make sense? Okay, so how much energy is required to melt 25.0 grams of ice at 0 degrees Celsius? Okay, so if you guys looked, there's a table. Ice is what? What is the chemical formula for ice? There's a table that was right. Four slides before this. What's the chemical formula for ice? All right, I can go with this. I want you to look. Awesome. What is the chemical formula for ice? Chemical formula for ice. What is ice? It's water, right? So the chemical formula for water is what? H2O. So we're going to look. I think it says H2O on there, right? Okay, so on your table, we're going to look for the heat of fusion for H2O. 333. Okay, so we know that the heat of fusion is 333, right? So we're going from a solid, right? Because it says how much energy is going to be required to melt, right? So it means that we're starting with ice, and we're going from ice to a liquid, to melting, right? So is my value going to be positive or negative? It's going to be positive. So we're going to use the positive formula. So we're going to use the fusion. Okay, so then we're going to say Q is going to be equal to what? What is Q going to be equal to? Q meaning the heat that's going to be made, the energy that's going to be made. It's going to be equal to give me the equation. This is what you guys think. We'll just talk about it. Are we going to use Q equal to M cap? That's the C, M, C, delta T, right? No, because we're not changing temperatures. We just want the heat of fusion. So then we're going to use Q equal to what? Okay, we're going to be using Q is equal to M times delta H. Fusion. Okay? So we know that that fusion is going to be a positive value, and we know that value because we looked it up on that table, right? Did you guys look it up on that table? You told me it was what? 333. So then how many grams are we starting off with? 25? 25 grams? Okay. So we have 25 grams. So then we just plug in 25 grams. And then we're multiplying it by 333 grams, joules per gram. So grams cancel out, and we're left with what units? What's the J again? Joules, okay? So 25 times 333. 8,325. If I remember, it's 25.0 grams. Okay, so then that's going to be joules. So how many sig figs should we deduct? 3 sig figs. Okay, so then my answer should be. And why is it 32, not 33?
Because we apply the same stuff.
Good job. Okay? Questions? Concerns? Yeah, that look.
But you can the answer, so it's 8325, and it's just 3, right?
We submit 50.
We don't round up,
Yeah, because that's exactly 5.
we don't round it.
So you wouldn't round it up, even though that person who did it here with me was wrong.
So,
But
so we do not round it.
nope. And so then that would be in joules. And on the paper, it actually says kilojoules. You can leave it in joules or kilojoules if it's a written answer, so you don't have to worry about either way. long as you're consistent. Right? I just want to make sure the numbers are consistent. Okay, questions? Concerns?
I don't know what we want.
Because it's exactly 5, right? Is there anything after it? Okay, so 5 is our breaking point, right? So this is like a teeter totter. So this kid over here weighs 5, and this kid over here weighs 5. Is it gonna go up?
No.
No, it isn't. It's gonna stay exactly where it's at. So that's the reason why we leave it exactly alone. If this kid over here is 5.1, right? Then what happens? It's gonna do this, right? Because that goes up, it's gonna do this, because this kid weighs more than this kid, right? So they're gonna round it up. Only if it's greater than 5. If it's exactly 5, we're gonna leave it alone. If it's exactly or less than, we'll leave it. Okay? So I need to fix that in my notes. Or I can just say, I did that on purpose to see if you guys would catch it. Okay, so we've already talked about specific heat. It was just basically showing what we just talked about, right? So this C is going to be constant, right? And you're going to be able to look them up. There's going to be a table for it in most cases. Or you're going to find it by experimentation, one or the other, right? So these are your specific heats. Now you'll notice that we have specific heat for different phases. So for instance, if we have a solid, our specific heat is one thing. If we have a liquid, our specific heat is something else. And if we have a gas, it is going to be something else. Okay? So I'm going to write these, our specific heats. So what is the specific heat for water when it's ice? So we're going to use the abbreviation for C. And we're going to use C and we're going to call it ice. So specific heat for ice. 2.06. 2.06. And the units are units. What are the units? What are the units? Where would I find the units? Where are the units? Where would I find the units? What are the units? What does that J stand for? Joules. The G stands for what? And the degree C stands for what? Celsius. Okay, so our units are joules per gram degree Celsius. Okay, so that's going to be the units of specific heat. My C liquid is what? For water? 4.8. Just do that. And our C gas. Okay, so here's my question for you. Okay, so the question says, how much energy must be released if 20.0 grams of vapor vapor starts at 30 degrees Celsius and is frozen to -5 degrees Celsius. Okay, so I'm gonna write the equations on the board. And then I want you guys to help me build this together in the pile. Okay, so we have Q is gonna be equal to M delta H. And then we have Q is gonna be equal to MC delta T. Those are the two equations that we're gonna use to construct this. Okay, so we have our energy diagram drawn up sort of, so I'm gonna extend it a little bit. Okay, so we're starting at what temperature? What temperature are we starting at? We're starting at 130 degrees Celsius. So we're starting up here, right? So this is 130 degrees Celsius. Okay? And then we're going down to -5 degrees Celsius. Okay? So we're gonna get it down to -5, so that's about right here. Okay? So if we take a look at this, well, first off, it says energy must be released. So what would we know about the value? What should our value be? It's going to be a negative value. So at the end of the day, the value should be a negative value because we know that energy is being released, right? So that's going to help us think about it. Okay? So where are we starting at? We said we're starting at 130, right? So if we're starting at 130, what phase are we in? Are we a gas? Are we a liquid? Are we a solid? We're talking about water. It's a gas. Okay? So now, since it's a gas, we're going to start off, that's going to represent this area here. So this area here is going to be, are we going to use this equation or this equation? Equation, we'll call this equation A or B. Those who say B, raise your hand. Which equation are you going to use to calculate the heat if we're starting off with the gas? Those who say B, raise your hand. Okay, those who say A, raise your hand. Okay, so now let me see if I can help you guys out. When we say A, we're only talking about the plateau parts, right? So you're not changing temperature. Are we changing temperature? We're changing temperature, so that means that you're going to use the one that has temperature in it, right? Does that make sense? So I'll ask the question again. Which equation are you guys going to use? A or B? B, okay? Because we're changing temperature, we're going to use B. Now here's the secret, right? Because we're changing phases as well. Because we're starting out at 130 degrees, which we know is a steam, right? Or a vapor. And we're going down and making ice. We're changing phases twice. So that basically means that we're going to have to use both equations, but at different points. Okay? So this very first step, from here to here, we're going to use Q equals M C, and C of what? Is it solid, liquid, or gas? If it's 100 degrees and above, then what is it? Is it going to be a solid, is it going to be a liquid, or is it going to be a gas? It's going to be a gas, right? So then should I be using C gas, liquid, or ice, or solid? Gas. Okay, so in this case, we're going to be using C gas. For our steam and our delta T. Okay, and you know our delta T is going to be final minus initial, right? Okay, so but here, instead of using the final temperature, right, we're only going to go up to 100 because this only represents the gas phase, right? Say, this only represents the gas phase. So we're only going to be able to go up to 100, and then we're going to be changing phases. Okay? Okay, so then let's go ahead and do that calculation. So we have Q is going to be equal to, our mass is 20.0 grams. Our C gas is what? 2.00, and that's joules, grams, degrees Celsius. So grams are going to cancel out. And then our change in temperature, we're going from, what is our final temperature in this case? T final. It's going to be 100. It's actually going to be 100 because we're only talking about this phase. Once we get to the lower temperatures, we're in different phases. So our T final is going to be 100 degrees Celsius minus 130 degrees Celsius. Okay, so then we get Q is going to be equal to you guys get. Okay. Negative. Okay. So that would be 3 sig figs. I'm going to put a bar over here to represent our 3 sig figs in this case, and our units are joules. Okay. So just for that gas phase, we know that we're going to need negative 1,200 joules. Right? So that's how much energy has to be released just for that gas phase. So then the next part is we have the hump, right? Or that plateau. What equation are we going to use for that plateau? What was it? A. That's right, we're going to use A. Okay, so then this here is for vapor, right? So if we're going from vapor, what is the opposite of vapor? If you go from a gas to a liquid, that process is called what? Condensation, okay? So you're right, condensation. So we're going to be using Q equals M delta H condensation. Okay? So then, what do we know about the heat of condensation and the heat of vaporization? What do we know about those guys? Anyone? Anyone? What do we know about them? What did I say about them earlier? Okay, so the heat of condensation, right, is going in one direction. If you guys take a look at it, do me a favor, go to page, but it is that. You guys go to page 13 and then slide 30, please. Page 13 and slide 30, please. For you guys. Slide 38 for you guys. Let me go back to it. Okay, slide 38, this slide. You guys see this slide? Right? So what does that mean? What does that mean to us? It says the heat of vaporization is going up in one direction, and it says exothermic. And then the heat of condensation is going around the opposite direction. And if you look at those arrows, aren't they about the same? There we go. Equal energy but opposite. Good job. So we know that they're equal energy but opposite. We have the heat of vaporization. So then what must be the heat of condensation? What is the value for the heat of condensation? It's simply the same, but opposite, okay? So heat of vaporization is 2.6 kilojoules per gram. So then the heat of condensation must be what? Heat of condensation must be what? If the heat of vaporization is 2.6 kilojoules per gram, then the heat of condensation must be what? Negative 2.6. Right? Because you said equal but opposite. Opposite turns to the side. So we have a negative 2.6 kilojoules per gram. Okay? So somebody do that heavy lifting for me. What do you guys get? Okay, so negative 52 kilojoules. Grams are going to cancel out. Okay, so then we're going from 100 degrees down to 0 degrees. So which equation should I be using here? You said B. That is correct. We're going to be using B. Okay, so then here we're going to be using Q is equal to MC. Now the C that we're using, are we going to be using ice, liquid, or gas? For sure. So we're going to be using liquid because it's in the liquid phase, right? We're going through the liquid phase. So now we're going to be using liquid. And then delta T. Okay? So let's plug it in. We have 20.0 grams. Our C value, 4.184. And that's joules per grams degrees Celsius. And then the change in temperature, we're starting at what temperature? 100. So then that's going to be our final, so it's minus 100. And then we're ending it at what temperature? 0. Okay, so if we do that math, what do you guys end up with? So we're going to call this Q lift. Sorry, my head in the way. Yes.
For the part, 4.1824, 4.18.
Because it's really 4.184, they just rounded extra. I just remember it from time. You could have used 4.18, that'd have been fine. What did you guys get for your Q liquids? Yeah, you guys say that one a whole lot louder. Negative 8,368. Okay, how many sig figs should we have? These are going to be. Six, how many? 3. Okay, 3 sig figs. So then, so then that's going to be negative 837. Negative 8,370. Okay, so then this is what we get for our liquid. And then what about our Q fusion?
We have to put the 0 for the answer, but it would be 7.
For your sig figs, yeah. You don't, well, yeah, otherwise if you don't have the 0 there, then it's gonna be 800, right? So you need that placeholder. Okay. So what about this line here? What about this line here? So this is no longer the heat of fusion, it should be the heat of what that we're looking at? Heat of what? Of ice, or heat of solidification. So we'll call it delta H. So we're gonna look at the Q of solid. Okay? So delta H solid. So then that's going to be equal mass times delta H solidification. So we're just going to say of solid. So our mass is 20.0 grams, and solidification are we going to use this formula for the ice? Sort of, we're using for that transition between going from a liquid to an ice. So we're only using it for this plateau right here. This is what we're using it for. Okay? So what is my delta H solidification? That's going to be equal to what? Because we have the heat of fusion, and we know that heat of fusion is going from, it's that plateau from a ice to a liquid. So then if I'm going from a liquid to an ice, then what should that value be? That's the heat of solidification. So if I'm going from earlier, right? You guys paid attention earlier. If I look from, so this represents the plateau, right? So this little bar represents that plateau. This here is my my liquid phase. This here is my gas phase. This is that plateau being over that hump, okay? So we said that for that value, you told me that we're going to use the heat of condensation, right? Because the process of going from a gas to a liquid is called condensation, right? Okay, so the heat of condensation, we said that that was going to be equal to what? What did you tell me it was equal to? The heat of condensation? Okay, so it was negative 2.6. So that 2.6 came from the heat of vaporization, right? So 2.6 is the heat of vaporization. Negative 2.6 is the heat of condensation. So if you look at that, what am I going to do in the case of going from a liquid to ice? I'm going to use fusion, but then what am I going to do to the side? Are we putting heat into it or are we taking heat out? So if we're going from a liquid to a solid, we're taking it out of it, right? Okay. So this is the thing, okay? This is really important. I know you guys probably this morning. Your boyfriend didn't give you a kiss this morning. Didn't give you your hug that you needed, right? Get over it. How did you come in? I just use your head, right? She's mad at me now because or she can get her Irish cream, you know, her Irish cream this morning. Or her Irish whiskey. Is that what it is? So no. Okay. So the thing is, you got to think about what you're doing, right? And I need you to think about it because that makes it easier for me. It also makes it easier for you if you think about it. Don't just sit here and look at me blank stares, right? Blank stares ain't gonna get you through this class. You got to come in with your head working, right? Okay. So you're right. You're right again. Again, you're right because we're making it solid, right? We're going from a liquid to a solid, so that's called solidification. So if that's called solidification, then, or freezing, right? We want to use just that opposite value. So what is the opposite value of 333? Negative 333, right? So you guys, you have it here. I need you to remember it and use it, okay? So if you do that, what value do you get? So our units are going to cancel, and then we're going to get Q delta H solidification is going to be equal to negative what? 20 times 333? Come on now, there's a thing. We just talked about using it. So what is it? 6,600. Okay. Way too many sixes. Okay. Okay, so then we're down to that last part, right? So we're going from 0 to negative 5 degrees Celsius. So if we're going from 0 to negative 500 degrees Celsius, what equation are we going to be using? Is that changing temperature? You said B. That is correct. We're going to be using B. So in this case, we're going to be using Q ice is equal to M C ice delta T. M still the same, 20.0 grams. And then our C, what is our value for our C ice? Value for C ice? C ice. And that units are joules, grams, degrees Celsius. So grams are going to cancel out. And then we're going from 0 to negative 5. So our final temperature is going to be we're going from 0 to negative 5. My final temperature is going to be what? Negative 5. My initial temperature is going to be 0. Okay? So if you do that math, Okay, so now the thing is, this is the energy of each of the parts individually. But we want to look at the entire thing, right? So we're talking about the total. So to calculate our total energy, Q total. So we know it's going to be Q gas plus Q delta H con plus Q lick plus Q delta H sol plus Q ice. Okay, now we want to make sure our units are all matching up. So they all need to be in joules or in kilojoules. Okay, so maybe the easier thing is to put them all in kilojoules or maybe in joules, right? So to change this guy to kilojoules, we just go here. That's 1, 2, 3. So then that's going to be negative 1.2 kilojoules. This guy here, 1, 2, 3. So then that's going to be negative 8.37 kilojoules. Okay, and then this one here is going to be negative 6.66 kilojoules. And then this one is going to be negative 0.206 kilojoules. Okay, so then we add them up. We have negative 1.2 kilojoules plus negative 52 kilojoules plus negative 837 kilojoules plus negative 6.66 kilojoules plus negative 0.206.
What is it, negative 0.2?
What's that?
Why is it like the last one, negative 0.2?
Because it was 1, 2, 3 to change it to kilojoules.
We always have to be.
Yeah, so because kilo is 1,000, so then it's 3 zeros, so you just move over back 3 spots. Match up those 3 zeros. Okay, so then your Q total.
It's 3 significant plus an additional.
Yeah, so when we add some up, line up the columns. Actually, we could get away with two safe days actually. So then you're right. So then we would just have it 68 kilojoules.
Could we go with decimals for addition?
Yeah, so we'd add them up, line them up. So then that would be the way it gives the significant So. After we do all the transition. Good job. Okay, questions? Concerns? Cash. The biggest thing is that the hardest thing to remember, right, is that when you're looking at it, you have to take into all of the different phases, right? If you only have one phase, it's real easy. You just figure out the equation that you need. If you're changing temperature, you're always going to use the one that says delta T. If you're not changing temperature, that means that you're at a plateau. That means that you're going to use that.
So it's one of two of those.
Yes.
Okay. And this depends on just a little one thing.
That's right. So I always draw my line in, that always has to be, right? Draw it out in. Okay? Yes, ma'am. So you said, yeah, so that was changing temperature, so that was just a plateau. That means you're in the process of going through different phases. You're not changing temperature, you're right at that point where you're changing phases. So like in the case of water, you're at 0 degrees Celsius, and you're just getting ready to change phase. So then that's the reason that you'll use equation A. Okay? Does that make sense? So the delta H is always when you're changing phases, right? And then when you have temperature, you're going through temperatures, then you're going to be using your the one with the delta T, right? Because it's temperature. Delta T can change temperature. So anytime you say we're going from here to here, you know you're going to have to use the change of temperature, right? Now, if it's in the same phase, then you only have to do that one block. But if it's in multiple phases, you have to break down each of the phases. And each of the phases are going to go through a phase change as well as the temperature change, right? So that's the reason why we have to take the total. Okay? Does that make sense? Okay, how's everyone? You guys go get your fix? You needed some sugar, because I knew it, I saw it in your faces. You're struggling here. Okay, so let's talk shop here, real quick. So, how are you guys feeling about this? Not good? Not work? Yeah, it's not hard, right? It's just long, right? And you just gotta remember, if you're here at the line, you're gonna be using your delta H, right? Let's see if I can.
So the end of the H, so what will be given to you?
So M is always max, right? So we always use M for max, right? So your delta H is typically given to you, right? It'll be into your problem, right? You don't have to memorize this. Your C's are going to be into your problem, unless you're figuring it out experimentally, right? So then that means that they're going to give you the heat. So you have to look at the equation, right? So you see what's missing, right? In most cases, if they're asking for heat, they're looking for the heat. Okay? If they're asking for the heat capacity, they want you to find the C, but they're going to give you the heat. They'll give you everything else. So look what's given you. These are your two equations. From these two equations, we should be able to figure out your right? So it goes with heat. Okay? So again, when we're changing temperatures, if they're saying we're going from this temperature to that temperature, right? Then you know that you're going to be using this equation. Now, if it's over different phases, if you're changing phases in addition to it, then you're also going to be using this equation, right? If they just say you're changing phases, we're going from a liquid phase to a solid phase, right? Then you're only using A, equation A. Okay? So as you see two temperatures, what are you going to think?
Changing temperature.
Changing temperatures, right? So we're going to use equation B, right? And then if you know that let's say you're going through multiple phases, right? Like this one here. This equation went through multiple phases. Right? So that tells me what? You're going to use both of them, but you just have to break it down. Break each phase down. Okay? Okay, good. Okay, so here's an example. How much energy is required to change the temperature of 25.0 grams of water from 10 degrees Celsius to 50.0 degrees Celsius? Okay, so what equation am I gonna be using? Temperature, right? So then we're gonna use our temperature equation. So we're gonna get Q is gonna be equal to MC delta T. Okay, so what C am I gonna use? What phase am I in? Or am I changing phases? 0 degrees Celsius to 50 degrees Celsius. What phase would that be in? Say it again?
Liquid.
It's gonna be in the liquid phase. So that means we only have one phase to look at, right? So then we only have to use this one equation, right? So then we want to use C of liquid. What is our C for liquid for water?
Four point three.
4.18, yeah, okay, so we're gonna go ahead and use that. Okay, so then we have our mass. Our mass is, ladies, our mass is 25 grams. C, you said was 4.18. And the units were joules, grams, degrees C. Okay, so then we know our grams are going to cancel out. And then our final temperature, 50. And our initial temperature, so Q is going to be equal to you guys get 4,180.
And 4.31 is gonna be 4,180.
Okay, questions? Concerns? Okay, let's move forward.
That one was so many steps because you went so far in temperature, but -5 to the 180.
Yeah, so that one shows us an example where we're going from multiple phases, right? We're starting off in the gas phase. So the example that we did earlier, we started off with the gas phase, we went down to the liquid phase, we went down to the solid phase, right? So that's the reason why it's multiple steps, right? This one is all in one phase, so then that's all you have to do for this one. There's nothing more to it. It's one phase. Sig figs, there's 3 sig figs, right? So if we do the math here, this will give us 3 sig figs right here when we take the difference. This one, 3 sig figs, 3 sig figs, right? So then it's just 3C fixed. So that's 4,180. That zero doesn't count as a significant figure, but it's holding in place so that we know that it's 4,000, right? Because if we don't have that zero there, it's 400. And that means something's not good. Okay, questions?
So 0 degrees Celsius, the Monday itself gonna be equal.
Yeah, so as long as it's below 100 degrees, right, then it's going to be a liquid. If it's above 100 degrees, we're talking about water, then if it's above 100 degrees, then we know it's going to be gas. If it's below zero, then it's gas. So that's that part. Remember, like, you got to think about it. Think about real life in that place. We know those things, right? We know when it freezes, we know when it boils, so we're got to use those things that we know about, right? You can't just turn off your head. And I know there's a tendency because you're like, oh, it's math. Oh my God, I hate math. Everybody wants to turn off their head when they see math. Not you. You're pretty good at math, I see, but you're not? A little bit, okay. Okay, so this is just showing you exactly what we just talked about, right? This is that curve that we talked about. And this is how you would use each of the steps, right? So you guys have already done this. You should be like, I own it, right? Because we just did that problem. Okay, so this is just taking you the algorithm of how to go about it, right? So just in case you don't remember, just go back here, right? Look at this, your notes, right? And so you want to do that breaking down of each of the parts. And it actually shows you the equation at the very bottom. You see that? At the very bottom, the equation that you'll be using down here. Right? At each of the different steps. Okay. So I'm gonna let you guys do this one, right? And then while you guys are doing it, I'm gonna do it on the board and then compare. Okay? Okay, so let's walk our way through it. So this time we're going from, we have 19.6 grams of ice, and we're going from minus 12 degrees to 115 degrees Celsius. Okay, so if we're going from ice to what phase would 115 degrees be in? What phase?
Yes.
It will be in gas phase, right? Okay, so are we expecting to have to put energy in to get it there, or are we taking energy out? Okay, so again, if I'm going from ice to a gas, am I gonna have to put energy in there? Or am I gonna have to take energy out of it? I'm gonna put energy in, okay? So then that means my value should be positive, okay? So immediately we say, okay, we should have a positive value, so we shouldn't have any negative values, okay? So if we start from the bottom, we're starting from minus 12 degrees, and we know that ice freezes, water freezes at what temperature? At what temperature, sorry?
0.
0, okay, sorry, I can't hear half the time. So we know that's going from a temperature change, 100. So then that means we're gonna use which equation, A or B? We're gonna use B because it says delta T, change in temperature, right? Okay, so we start our temperature, our final temperature is gonna be 0 degrees, and our initial temperature is gonna be minus 12. So minus times a minus is a positive. So in other words, we have 12 times 2.06. We got our C value because from that table earlier, times 19.6. I forgot my units. Right? So look at our units, grams are going to cancel out, C's are going to cancel out, and then I'm left with just joules. Right? Now, I know that I'm gonna probably have something that's in kilojoules, so then I'm gonna change it to kilojoules by counting over 3 spots. So that's 1, that's 2, and use a different color. You guys can go. You guys can see it. So that's 1, that's 2, that's 3 spots. Okay, so we're moving over 3 spots, so then it's 0.48. We know we have 2 sig figs from our 12 here, right? So then that's how we're gonna end up with 2 sig figs. Okay, so then I'm just gonna go ahead and put that down here for my ice value. Okay, so you guys see that at the very bottom? Good. It starts. Okay, so that's what I'm putting right here. For that value. Okay, so then the next part. Now we know we're going through a phase change. So we're starting off at ice, and we're going through a phase change. So when we go through a phase change, we're still going to be at 0, but we're going from ice to now a liquid. So then what equation are we going to be using? Yeah, so we're going to use equation A. So where heat is equal to N times delta H. So that process of going from a solid to a liquid is called fusion. So then we're going to use the heat of fusion. So then it's going to be mass times delta H fusion. Well, we know our delta H fusion is this value. So then we're just going to multiply our mass times 333 joules per gram times 19.6 grams. And then we're going to end up getting 6,526.8 joules. But we know that we need 3 significant figures. I'm just going to go ahead and change it to kilojoules, so it's 6.53 kilojoules. And so then I'm going to put that down here as well. So then that represents my delta sol, not my sol, but my delta fusion. Okay, so that means we've gotten this one done as well too. Okay, so our next one is we're now in the liquid phase. Now the liquid phase starts at what point? Starts at 0 and it'll go all the way to 100. So that would be our liquid phase. So since we know our temperature is above our liquid phase, the final temperature that we want to get to, which is 115, that's above our liquid phase. So then in that case, we know we're going to go from 0 to 100. So then we're going to go and use MC delta T. And then in this case, we're going to use the C liquid. Okay, so then that's going to be 19.6 grams times 4.184 joules per gram Celsius times our final temperature is going to be 100, our starting temperature is going to be 0, and so then that's going to end up being 82,006.4. We know that we're going to have 3 sig figs in this case, so then we're going to end up with 82.0 kilojoules. Again, I just converted directly from joules to kilojoules. And so then that's what I'm going to put here.
Is it wrong on the paper?
What was that?
Is that one incorrect on the paper?
It's the same. 1.89. Maybe let me just recap. So. I might have messed up. I might have. So 19 times 4 times 100. So that's 0. 4 is. You're right. It should be. I got carried away. So. So it'd be 8,264. Okay, that's because you guys are using this value here, right? So what did you do? Yeah, 8,000, okay, so let me fix that. So I use a slightly different value, so my value is a little bit higher than yours. It's not gonna make too much of a difference. So at the end, then we'll go 1, 2, 3, until we end up with 8.2 in my case. So then that's what we're gonna use down here. So thank you for correcting that error. Then I recalculate the numbers. Which one is? The total? Is it 74.4?
On this paper, it always has a 1/1000 at the end, we don't have to do that. 1/1000.
That's just a change of units from kilojoules to joules.
Okay.
So that's how we do it.
Okay.
Okay, so then if we go for our next one, right? In this case, it's just the heat of vaporization. So here we're gonna have the heat of vaporization. So then we're gonna have 19.6 grams times 2.6 kilograms per gram. And so you're gonna end up with 50.96. So that's just 51 kilojoules. And so then that's what I put down here. And then at the very top, we're going from 100 degrees to 115 degrees. And I remember I was actually taking an exam for, I can't remember, it was for some class. I think it was for grad school when I was trying to get into grad school. And I had this problem, and I had a nightmare about this problem.
It's just slightly off, like, it's because it changes the whole outcome, is it gonna be wrong, or is it zero?
No, if I see your work, it'll be fine.
Oh, it's like just the point.
So you just.
I'm really bad at
Somebody do this math, do this one for me.
yeah, that one I got something.
Was that 8.2? So we have 0.59 plus 0.51. 8.2. 6.5. Okay, so I got a different value than we do. 66. There, feel good. Oh. Okay, okay. So let me recalculate. 0.9 plus 51 plus 8.2 plus 6.53 plus 66.8.
Where'd you get the 140?
Where did I get the 140?
The total one?
Oh, yeah. It was when I made a mistake. So it should be 66.
So you said the C ice value is 4.18.
Yeah, so the C liquid.
Liquid,
Yeah, it's 4.184.
So that's gonna change my thing, so.
It doesn't have to be, so the thing is, you look at your value.
My end is, I just
60.
know.
Yeah. So it changed your value by a little bit, overall, it's not gonna make too much.
Okay, as long as we do this, then.
And you show me, that's it. And so usually, we'll give you the values for C, you just use those values, until you'll be okay.
They're saying the C's will be given to us.
Yeah, so typically on the exam, your Cs are gonna be given to you.
Okay.
And so like if you guys have done this exam, if you've already done it, the C is given to you.
So this is the C chart of the C's, right, and this is the tuition one.
That's,
Yeah.
okay?
And you're the oldest receiving the.
Why? No, sometimes you're gonna be using I. You need to pay attention to what you're using, right? And then in that case, they'll tell you, if you take a look, it also tells you the order points, right? And so you'll know the order points and your freezing points. Yeah, that's right.
And that chart is not.
Yeah. No, it isn't on there. So, but typically, it's given to you on the exam. They give you those values, right? We don't assume that you know where iron boils. Okay, so don't overthink it, right? And you gotta be adaptable, right? Because you're not always gonna get water. Sometimes you may get metal, or you may get, so you gotta be adaptable. It's the learning the concept, the big picture. Okay, big picture. Okay, questions? Concerns? Are there any concerns? What, A, what about it? It's only, let's go back to the table. So if you take a look at this, right? When it's flat, right, that's when you use it. So when you're going through phase changes, so if they tell you you're going from a liquid to a solid, that's a phase change. That's the time that you're using it. And typically, they're not going to give you a temperatures, right? Unless you're doing overall. But when you're doing overall, you have to take into consideration phase changes as well as the temperature change. So you're using both, okay? So anytime that you see two temperatures, you know you're going to be using the Q is equal to MC delta T, right? And then if they just tell you you're just changing phases and they don't say anything about temperature, right? Then you're going to be using Q equals M delta H, okay? Okay. Okay, so we've already talked about you and your boo, right? And the concept of exchanging heat, right? And so if we have something that's high and we have something that's low and we put them together, they're going to meet somewhere in the middle, right? So they're going to get to what we call temperature equilibrium. They're going to form equilibrium. So if you guys snuggle long enough, what will happen is that you guys are going to meet somewhere in the middle, okay? So you're going to meet in an equilibrium. Okay, I shouldn't have to talk over you guys. Okay. I know that some of you guys are still working on the problems and helping each other. That's fine, but I shouldn't have to talk over you. Okay, this is not high school. If I have to do that, just don't come. Save me the time. Okay. So, law of conservation. So we've been talking about the law of conservation. Law of conservation of energy and mass. It basically is essentially the same thing. At the end of the day, what you put in, you have to get out. It has to be accounted for. Either we're putting it into the system and it's being stored into bonds, right? Or in the case of mass, what we put in when we get out, remember when we were balancing chemical equations? If you put in 4 carbons, you got to get out 4 carbons, right? Law of conservation. Okay, so you guys want to remember the law of conservation. That keeps us honest. Okay, we've already talked about the heat of reactions, right? So that is also called enthalpy. enthalpy. And we can apply this to chemical reactions, because they're going to behave very similarly, right? So here's an example. If we look at this chemical equation is called a thermochemical equation. In this context, we have a negative value for our delta H. What does that tell us? Are we putting that in the reaction, or are we taking it out of the reaction? We're taking it out, okay? And so if we look at our chemical equation here, right, we have ethane reacting with oxygen, and it's going to make carbon dioxide and water, and then we're releasing, right, 2,855 kilojoules. So we can also write the chemical equation in this form, right? And so where we actually put it as part of the chemical equation, and we put it on the product side because energy is being released, right? Or, yeah, energy is being let go, it's exiting, okay? So in the case of, if we have to put energy in, we know that it has to be a positive reaction, right? And then, so we know that this is an endothermic reaction. So in this case, we put it on the reactant side. Do you guys see that? Oh, I'm not even, right here, we put the energy on the reactant side. Do you guys see that? Where up here, we put it on the product side because it's an exothermic reaction. Energy is being let go, right? So we're not putting it into the reaction, we're releasing it. Okay, so to make this happen, this energy happen, or make this reaction happen, we have to put energy in. So then in this case, it's on the reactant side, right? So if we're going from ice to liquid, are we putting energy in, or are we taking energy out? We're putting energy in, right? So we have to add energy to make that happen, right? So then that would be on my reactant side of the equation, right? So that's when it's endothermic, we're putting energy in. So that means it's on the reactant side of the equation. When it's exothermic, we're taking energy out. Does that make sense? Okay, so what I'd like you guys to do is, here's the description of the chemical equation, right? It says, a thermal decomposition of limestone solid calcium carbonate. And so this is calcium carbonate. And then this here is our limestone, okay? I'm sorry, this here is our lime. So then this is gonna be solid calcium oxide. And we're gonna form gaseous carbon dioxide, okay? So these two are our two products. So this is what's decomposing. So that is gonna be our what? Reactant or product? This is what we're putting into the reaction. This is what we're getting out of the reaction. Oh, sorry. One day I'm gonna get this right. Okay, is it short now? You can see it now. Okay. So we're putting this into the reaction. This is what we're getting out of the reaction. Okay, so reactants are gonna be what? What is, okay? So then our reactant is gonna be CO3. And it's a solid. And then our products are gonna be And gas is gas. Okay, is it balanced? Sure. How many carbon, how many calciums do we have? Was that? Okay, it is. Okay, so we got a total of 3 oxygens, we have 1 carbon, and we have 1 calcium. 1 calcium, 1 carbon, 3 oxygens. Okay, so we have a balanced chemical equation. So it meets the conservation of mass. And then the next thing it says this is an endothermic reaction, okay, where we have 178 kilojoules per mole. So am I going to put that on my product side or on my reactant side? On my reactant side. So I'll put it over here. And normally, even though earlier we have, normally we'll put per mole or per gram, right? Because it has to have that unit. So our delta H should have either moles or grams on the bottom. That's plus. It doesn't look like a H there. Okay, so that would be one way of showing it. The other way of showing it is just writing the chemical equation and then putting delta H. It's going to be equal to 178 kJ per mole. So we know it's going to be a positive value or a negative value? Positive. Okay. And then you can just write the equation independent of that. Okay. Questions? No questions? Good. Okay. So the last thing that I want to show you guys is how are you going to use this? So once you get the equation, how are you going to be able to use it? Or how are you going to be able to use this to sit there and figure out how much of certain things that we have or how much energy we're generating? Okay. So the question here says, what is the mass of liquid octane C8H18L, a component of gasoline, must be burnt to provide 9.05 times 10 to the 4th kilojoules of heat. Delta H of our reaction is going to be equal to negative 5,471 kilojoules per mole of octane burnt. Okay, so what do we know about heat? What is the what equation would we use in this context? Do we have a temperature change happening? What was that? We do have a temperature change? Do you guys see a temperature change there? Did they say anything about a temperature change? No? So if there's no temperature change, what is the equation that we would probably use? for heat? What is that equation for heat? What are our two equations for heat? What was that? It's A, that's right. So we know they're going to be using Q is equal to the mass times our H. Okay, now the difference is that if we look at our H here, this is in mass, it's in moles, right? So we need to figure out a way of changing our moles to mass. So I'm going to introduce you guys to the molar mass. So. Okay, now if we are trying to figure out the molar mass, we take a look at our chemical compound. How many carbons do we have? Okay, so we have 8 carbons. Okay, on your periodic table, how much does each carbon weigh? Okay, and that's going to be grams per mole. And then we're going to multiply that by 8 times 8. Okay, so that's going to equal 96 point something. Okay, and then if we talk the hydrogens, how many hydrogens are in octane?
18.
So we're gonna have 18 hydrogens.
Which is to 1.508.
Grams per mole. So what is that, 18? Point. So,
18.1.
okay, so then we're gonna add these two together. Two. Two. All right. Okay, so we know that this is the value that we have per mole. We know that 1 mole of, let me see, I'm gonna break this out right, of our C18, I mean C8, 18. So this tells us for every 1 mole of C8, H18 is going to be equal to 1, 1, 4.233 grams. Okay, so then if we're trying to calculate the mass, and this is how much, this here's our Q value, so this is going to be equal to Q. So then we know that Q is going to be equal to 9.05 times 10 to the 4 kilojoules. And then that's going to be equal to our mass. And then we have what our delta H is, which is 5.471 kilojoules.
Is it also negative there?
So in this case, we're gonna say, because they're trying to calculate mass, and we're not gonna have, you can never have a negative mass, right? So we know that we're talking about the energy that has to be present. So then we're gonna make it a positive value in this case. It's gonna be understood to be positive, because you can't have a negative mass. Okay, and then that's over 1 mole, right? But we know that we want mass, we don't want moles. So we're gonna use the fact that we have 1 mole is equal to 114.233 grams to change to grams. We're just gonna go ahead and do that. So 1 mole is on top. And that's gonna be 114.233 grams. Bless you. Okay. So then what we're gonna do, we're gonna solve for n. And so we're gonna get n is gonna be equal to, so if we bring all of this to the other side of the equation, the inverse of it, so you're gonna get 9.05 times 10 to the 4 that's going to be divided by 5471. We know that here the moles are going to cancel out, so we're not going to even worry about bringing those over. And then, and that's KJ. Then we're going to multiply that by 114.233. So then we're gonna end up with, the kilojoules are gonna cancel each other out. And we're gonna end up with 1,800, and I should have 3 sig figs and 90 grams.
I usually multiply the 10 by the 4. It's 4 zeros.
So, yeah, so it'll be, you'll move it over 4 zeros, 4 spaces, so it'll be 90500. Or you could just go, if you just put in 9.05 EE, you guys remember when we talked about that EE? Okay, questions? Questions? No questions?
We have 4 times 10 to
You have to put times 10 to the,
That's, we'll get this.
yeah, so you can actually, you don't have to put it in decimal form. I mean, if you want to sit there and write out thousands and thousands of zero, more power to you. This is a small number right here, the 9.05 times 10 to the 4th, that's a small number. You're gonna get numbers that are gonna be much bigger, they're gonna be 23rd, 24th. So you wanna get in the habit of using that EE. Okay, so don't try to escape it, you need to learn how to use it. Don't run from the problem, fix the problem, right? Does that make sense? Yes, you can use the calculator on your tests. Yes,
For the moment,
how did I get, for the molar mass, how did I get what? Yeah, because it's, so we have 8 carbons, right? So then it's 12.001 times 8, right? And so that should be 96.088. Is that right?
yeah, this is a big break up to 12.0 from that. Off the chart.
The periodic table. Yes, so, yeah, so when you're talking about molar mass, you're always getting your masses from your periodic table. That's how much they weigh. Okay, so we're gonna use the periodic table to get that.